Okay, hello everyone, and welcome to this evening's public lecture, which will be given by Seth Moran of the USGS Cascades Volcano Observatory in Vancouver, Washington. Before I introduce Seth, though, I'd like to draw your attention to our next public lecture, which will be on March 22nd. It's entitled Snow and Avalanche Science, Highlights of Applied Avalanche Research and Forecasting by Eric Peach of the USGS. Now, we are very lucky to have Seth Moran here today, who is currently serving as a scientist in charge of the USGS's Cascades Volcano Observatory in Vancouver, and he's been in this role since 2015. Seth's volcano career began in 1974 when his parents took him as a 7-year-old to see the still steaming year-old lava flows erupted in 1973 by Eyjafjallajökull volcano in Iceland. A wonderful public library continued to feed his interest in volcanoes and earthquakes while he grew up in the decidedly non-volcanically active area of Amherst, Massachusetts. He began to sink his teeth into volcanoes for real at Oberlin College in Ohio, where he earned a degree in geology in 1988. And then realizing that rocks weren't quite his thing, he shifted over to seismology for his graduate studies, earning a master's and PhD degrees in geophysics from the University of Washington in 1992 and 1997 for studies of seismicity at Mount St. Helens and Mount Rainier. In 1997, he was hired as a volcano seismologist by the USGS's Alaska Volcano Observatory in Anchorage, where he spent 6 happy years studying and monitoring Alaskan volcanoes and also learning how to skate ski. In 2003, he moved to Vancouver along with his wife Elisa and 2 kids, Shannon and Sarah, to take a job as volcano seismologist at the Cascades Volcano Observatory. Mount St. Helens began erupting a scant year after his move, an unexpected 3.25-year-long eruption that absorbed much of his time between 2004 and 2008, and from which many lessons are still being learned. And while not spending time at work or with his family, Seth plays fiddle in a bluegrass band. So, so without further ado, here is Seth.
Thanks, Jen.
Canada or Vancouver, Washington?
Thanks, Jen. So just to clarify, CVO is in Vancouver, Washington. And thank you all for coming tonight. And just want to start off by making a declarative statement that I love my job. And the job title is cool sounding, scientist in charge. And what that often means is in charge of herding cats. And there's not as much in charge as one might think. But 2.5 years ago when I took this job, I didn't think I was ever going to say, I love this job. And that's because it's a management job, and there's a lot of personnel things and budget things and rules things and having people get unhappy with you, and all that is happening. And also, before this job, I did research as my primary job avocation as a volcano seismologist, and I thought that would end, and in fact it has. And so despite those things, there's another part of the job that I'm finding really interesting, which is the main part of the job is facilitating science, and that's the science in the observatory and also across other groups. And what that means is that you have to understand people's science so that you can prioritize research directions in the observatory, so that you can prioritize where money is going within the observatory, and so you can also advocate for your researchers' science and also take it out on the road and present it to other folks in a way that is compelling. And all that requires somewhat of an in-depth understanding of what everybody is doing. And so what I've found is that in the course of trying to get good at this job, I've had to learn what all these other people are doing. And it's been really fun. The scope of work in the observatory, I sort of had an idea what it was, but mostly I was spending my time as a volcano seismologist in one little corner. and didn't really think or learn that much about this. And so that part has been really fun. And so what I'm here to talk to you about tonight is what I've learned about the Cascades Volcano Observatory, who we are, what we do, and why we exist. And I know that none of that is in the title, and you could accuse me of false advertising, but there's a hook. And the hook is that the part about why we exist, we are funded by taxpayers. And anybody who is funded by the public needs to be able to explain why it's important for the public to be doing that. And in our case, in the Cascades, we have something of a challenge because we get eruptions about two times a century, once every 50 years or so. And that's the definition, or one definition, of a low probability, high consequence event. And 50 years is about enough time for 1.5 generations to, this is going to sound weird, don't take it the wrong way, but to rotate out. And that's long enough for people to forget what's happened. And that's starting to happen with Mount St. Helens right now. It erupted in 1980, and we're 38 years after that. And now, when I go out, more people that I meet weren't there in 1980, either because they hadn't been born yet, which is still hard for me to get my mind around, or because they moved into Portland, like from California. I don't know why anybody would want to move from California, but so it's just we're starting to see that happen at St. Helens, and one of the things that we're having to do is tell the story. So anyway, long story short, that's the sort of scope of tonight's talk is to introduce you to the folks I work with and where I work. And here are the folks that I work with. This is you can see fairly happy group of people. Happy because we know that if we don't smile, we're going to have to stay outside in the cold for another couple of shots. And but also people pretty much generally enjoy working there. We were born in 1980, basically, with the Mount St. Helens eruption. Before that, there was no USGS office that was looking at volcanoes specifically in the Pacific Northwest. When St. Helens erupted, it became very clear that this was a multi-year thing and there needed to be a permanent presence. And so that was formalized in May of 1982. So that's our origin story. We are one of 5 observatories that are operated by the USGS. There's also the observatory here in Menlo Park, the California Volcano Observatory that has jurisdiction over California and Nevada. The Hawaii Volcano Observatory is the oldest observatory. 1912 is when they started, were officially anointed. Alaska Volcano Observatory has all of Alaska. They came into being in 1988. And then finally there's the Yellowstone Volcano Observatory, which has Yellowstone and then a lot of other volcanoes in like New Mexico and Utah and California. So there's 5 of those volcano observatories. This next fact is boring, but it's there for a future acronym that you'll see on a future slide. So we're organized under something that's called the USGS Volcano Science Center. And that's the umbrella under which all of the volcanoes are monitored and all of the volcano science activities are sort of administered. It's called the VSC. Those observatories cover all of the 160 active volcanoes in the United States. And by active, what's meant is that there's been something that's come out of the ground in the last 10,000 years. So it could be just once. And there's a couple that slide in not quite under that definition, like Yellowstone hasn't had something in tens of thousands of years, but it still counts as active. And then out of that, there are 18 that are considered to be very high threat. And I'll explain what I mean by that a little bit later on. But that's the overall context in the United States in which the Cascades Volcano Observatory is operating. So a little bit of who all those people were in that picture I showed you. In our building, there are 85 folks, at least the last time I walked around the offices and counted. And those break out into a lot of different projects. And there's one project here called the Volcano Disaster Assistance Program, which is our international group that works with other countries to help develop capabilities, to transfer knowledge, and also for us to gain experience with active volcanoes in other places, and we can bring that experience to bear back into the United States. So that's a fairly healthy program, 15 or so folks. We also have a fairly healthy group of retirees that are still working, which is great. And then there's things like our admin wing for the entire Volcano Science Center. Most of them are based in Vancouver. We have a volcano emissions program that works across many of the observatories. Our web presence, the number of the folks that manage that are there. And as of October, we have the Yellowstone Volcano Observatory Scientist in Charge, located at Vancouver, Washington, which confuses lots and lots of people. But that's just where his office physically is. So out of all of that, there's the CVO project, which has 31 people. And I'm counting things in ways that some other people might count things differently. In truth, there's a lot of bleed over between, say, VDAP and the CVO project. Some people in CVO work for VDAP and vice versa at different times. But 31 is the rough number. So that's a lot smaller than 86. And this is how the CVO project is broken out. It's roughly into half research and half research support in terms of making instruments work, in terms of doing all the IT stuff, keeping the facility working, and also outreach. So this is also a little bit boring, I recognize, but the point of this is that there's about 30, 35 folks that are working in the Cascades. And sometimes people look at all the people in the office and they go, well, why do you need all these people? And the answer is we don't have all those people, although it would be great if we did. The job descriptions are really varied, which is one of the fun things that's about working for a volcano observatory. I have this, bring this slide when I'm talking to like career fairs and middle school students who are interested in STEM careers. The point being, you don't have to like rocks to be a volcanologist, nor do you have to necessarily be a PhD scientist. There's all these different things. We need people who understand computers, who understand IT, who are really good at admin. Wow, do we need good people who are administrators, because the bureaucracy we deal with is pretty immense. And outreach specialists, and as well as geologists and geochemists. And one of the also fun things about working at an observatory is that these folks, we all have our offices next to each other. And so I can go across the hall as a seismologist and talk to a geochemist and have actually a pretty good conversation where we sort of are kind of speaking the same language, the volcano language. Whereas in a university that can be kind of hard to pull off, because oftentimes they're in different parts of the campus and they don't necessarily have that common language. So that's another one of the fun things about working at an observatory. In terms of the Cascades, now I'm sort of going to set the stage for the geography of where we work. This is a map that shows all of the triangles in the western United States, places where magma has come out of the ground in the last 10, 12,000 years. That red circle shows where we are today. That's actually, it's a lot of it. It goes from San Jose to San Francisco. It's a really big circle. But up here is this line of triangles here is the Cascade Range, and it has some volcanoes that you've probably heard about, like Mount St. Helens, which is located right there, and Crater Lake, which is located in southern Oregon, and where the geologic story has really been unraveled and told by Menlo Park geologists, including Charlie Bacon, most famously. And then there's volcanoes you probably haven't heard of, like Glacier Peak, which is located right smack in the dab of a really dense wilderness with lots of tall, old-growth trees. And it's also one of the more explosive volcanoes in the Cascades, and that's one that we are constantly thinking about. How can we monitor it better? And I'll tell a story about Glacier Peak a little bit later on. And then finally, there's one that probably nobody's heard of called Diamond Craters. So runs the gamut from famous to not so famous. There's also a stretch in here where you can have a really good day. And that stretch is right there. My definition of a good day is a 10 volcano day, when you can stand in one place and look out and see 10 volcanoes. And actually, there's another volcano off to the left of this that I just couldn't get in the camera view, which is called Newberry Volcano. So there's a lot of volcanoes, and that's one of the really cool things, especially about Central Oregon. And to to continue the cool story, here's Portland, and here's CVO. This is where we're located. And all of these patches and circles are vents from the boring lava field. Portland is the only major metropolitan area in the United States that has an active volcanic field in its midst. These little vents pop off about every 15,000 years or so. They've been doing that for several million years. The most recent one was about 57,000 years ago, so by one metric, you could say we're overdue. Was supposed to be ominous. We're overdue. So we're in the midst of this. We actually have a local volcano near us, about 5 or 6 miles away is Green Mountain. That's CVO's little local volcano. And so there's a lot of things to be excited about in terms of volcanoes in the Pacific Northwest, and that's probably the reason why there's so many really cool beers named after volcanoes or volcanic features. But I digress. Back to CVO. So our turf is Washington, Oregon, and Idaho. That's the place where we're sort of supposed to be primary and focusing on understanding the volcanoes better and monitoring and mitigating. That's not to say that if something gets cooking, that we would not bring in people from other observatories. For sure, people from Menlo Park, for sure from Alaska, for sure from Hawaii. We sort of have a mutual aid understanding amongst all the observatories that once an eruption really gets going, it's hard for one observatory to take it all in. So in our authoritative area, at least in Washington, Oregon, there are 25 places where magma has come out of the ground in the last 10 to 12,000 years. And I mentioned this before, this very high threat thing. There's 8 of the 18 very high threat volcanoes in the United States that are located in Washington and Oregon. And they go Mount Baker, Glacier Peak, Mount Rainier, and Mount St. Helens in Washington. And then they go Mount Hood, Three Sisters, Newberry, and Crater Lake in Oregon. So what is this very high threat thing? Well, threat is another synonym for risk. And this comes out of a study that was done by the USGS in 2005 that looked at 2 factors. It looked at the volcanic hazards, which is what can happen at a volcano. Can it erupt explosively? How frequently has it erupted? And other things like does it produce large mud flows? And then there's the vulnerability or the exposure. Is there anybody in the way? And if so, how many of them? And also what type of infrastructure is in the way? And that's all factors into the exposure score. So you take those 2 and you combine them, and out pops a number that allows you to relatively rank all of the volcanoes in the United States. And so that was done back in 2005, and out of the 160, there are 18 very high threat volcanoes. 8 of those are in CVO's turf. And so that's what those red triangles on that map show. In the Cascades, I mentioned this before, there are roughly 2 eruptions per century. And to put this in perspective, in our neck of the woods, the big thing that everybody's worried about is the big one. Down here, the big one is at San Andreas. Up in Washington, Oregon, and Vancouver, or British Columbia, it's the big one of the Cascadia earthquake, which is going to be like a magnitude 9 thereabouts. The last one happened in January 1700. They happen about every 450 to 500 years. There's a little bit of controversy about that number, but roughly speaking, 450, 500. And so in between those big earthquakes, and the next one's going to be a huge consequence. There's no question about that. But in between those 2 earthquakes, there are going to be 9 or 10 eruptions in the Cascades. Somewhere, we don't know where, but somewhere in the Cascades, 9 or 10. And each one of those is going to be a lot lower consequence than the Cascadia earthquake, but they're still going to be big consequence. That's one of the things we learned in 2004 with Mount St. Helens when we had a really, really small eruption, and for about 3 weeks it paralyzed the West Coast in terms of the media attention and all the people that were really just following the thing and taking down websites because they were just pinging it too many times with data information, and people were also out of the volcano trying to see an explosion, and created this person issue because there were 5 miles of roadways where people were camped along the sides and there were no services out there. So how do you deal with that for a couple weeks? Even for really, really bitty eruptions, there's a lot of consequence, and that's something that we need to be telling the story about to make sure that communities around the volcanoes are prepared for. Okay, so that's sort of the rough context of CVO. And now I'm going to dive a little bit deeper and go into how we organize ourselves, or how sort of the areas of focus of our work. And there's really three of them. First is research. The second is monitoring. And the third is community preparedness. And that last one is in some ways the hardest one, because a lot of us come out of a research type of program, and there's nothing in those programs that prepare us for what's really more a social science kind of thing about the effectiveness of messaging and what are the best practices for talking with folks that are coming from a lot of different backgrounds. But that's the Volcano Observatory in the middle of all that, and all of this is in the context of external partners. So we have on the community preparedness side of things, we have external stakeholders from counties, the state, things like that. And then also on monitoring and research, we have a lot of academic colleagues that are working with us as well. And a lot of this is true also for Calvio down here and many of the other observatories. So I'm just going to give quick examples of each of those. Research, a really sort of rubber meets the road example of the importance of research is establishing eruption histories. So this slide here is from 2000, and it shows all of the eruptions that have happened in the Cascades over the last 4,000 years, going from 4,000 years ago to the present. And each one of these icons, there's good reason for believing that magma did come out of the ground at that point. So one thing you can do in terms of assessing a hazard is to just count the number of icons, and that gives you your rate. So based on that, Mount St. Helens is the most frequently active, and then it goes to Glacier Peak as number 2, and then you come down to California, Mount Shasta number 3, Medicine Lake number 4, and Mount Rainier number 5. Now, since then, a number of geologists have spent time at Mount Rainier doing some fairly careful fieldwork and have discovered evidence for small eruptions, but definitely eruptions that were not known at this time. And so when you bring those into the picture, all of a sudden Mount Rainier pops up to number 2. There's a lot of eruptions that were added in the 2,000, 3,000 years ago. So that is an important data point to be able to give to our partners. And this, again, comes back to even if it's a small eruption, it's still a high consequence eruption, particularly locally. All of them matter. I'm going to zoom in on Glacier Peak now and give you another for instance of how this matters. So Glacier Peak let loose a really large eruption about 13,500 years ago. This is a deposit that was left by that eruption that's 100 meters thick. There's a person for scale right there. And this is a couple miles away from the volcano. So this is a lot of stuff that came down. And just for perspective, this is a map that shows the distribution of ash fall from a couple of really large eruptions. So here's the Yellowstone, the most recent eruption, 600,000 years ago. This is its expanse, goes off the map. Long Valley here in California, also a very big eruption. Crater Lake in Oregon, also a fairly big one. Here's Mount St. Helens, this little tongue, 1980, much, much smaller than those other ones. And then here's Glacier Peak from 13,500 years ago. It's quite a bit bigger than Mount St. Helens. And there's a good question about how often should we expect those kinds of things. And that's where the geologic record is important. It turns out they're not very likely. They're not very common. So here's a timeline going from 15,000 years to the present. And this is that one outlier. And then here are 4 or 5 instances where we know magma came out of the ground. Those are much, much smaller eruptions. In fact, they're much smaller than Mount St. Helens 1980. They're about a third to a quarter the size. And so this becomes important because we need to be able, in certain instances, be able to tell people what we think is the most likely thing that's going to happen. And in this case, what we would say is that based on the last 10,000 years, the most likely thing to happen is an eruption that's not that big. This factors in to things like estimating, to providing information about ash hazards. So one question people sometimes ask is, should I be thinking about ash falling on me? And I've put this question more directly. What are the chances of measurable ashfall in Seattle? So this plot right here is output from a fairly new model that has been put together by Larry Maston from our office that takes an eruption of a certain size and puts it in the air and then brings in wind fields that come from the National Weather Service. And the wind fields push the ash in certain directions, and then the ash falls in this model, and he's able to track the thickness, how much piles up in different places. And what this map shows is the result of doing that kind of modeling for 1,000 different days with 1,000 different wind patterns. And he watches where they go and then compiles statistics for a millimeter of ash, which is about 0.04 inches of ash, basically measurable, what's a measurable amount of ash. And so what these contours show is that in Seattle, if there was an eruption at Glacier Peak, there would be a daily chance, about 1%, of a millimeter of ash falling on Seattle, which would be a pretty big deal if a millimeter fell on Seattle. There's a lot of steps in that. It's what the statisticians call a conditional probability because there's a couple of probabilities involved. The most likely eruption is a small dome collapse. There's been 4 of those in the last 10,000 years. So it's 1 in 2,500 for a yearly average. And then here is the eruption happened. What are the chances that winds would be blowing towards Seattle? That's basically encapsulated in this 1%. And then put all that into an ash model. And there's the answer, 1% chance of a millimeter of ash in Seattle if there's an eruption. So turning that into a number, it's a 1 in 250,000 annual chance or 1 in 91,250,000 daily chance. That's the 2 probabilities together, the probability of eruption and the probability of ashfall. So to put those in perspective, Powerball odds are about 1 in 292 million. So it's more likely than winning the Powerball on a daily basis. But getting into a car accident, it's about 1 in 5,500. So when you're trying to stack up all the things there are to worry about, car accidents are the thing that's more likely to happen to all of us. Everybody gets into 4 accidents in their lifetime, which is a depressing statistic. So drive safe. So next thing is going to monitoring. And the principle of monitoring is that when magma moves towards the surface, it breaks a pathway, it releases gases, and the chamber may increase in volume or decrease in volume. And each of those things results in phenomena that we can detect with instruments at the surface. We can see earthquakes with seismometers on the surface. We can detect emissions of magmatic gases, particularly SO2 and sulfur dioxide and carbon dioxide. And with GPS instruments, we can see if the ground is rising or falling. And so that informs a strategy, which is that we need to have instruments on the ground. And we've learned through experience that it's important to have a lot of instruments in the ground. How many? In this case, arguing for 12 to 20, which is an awful lot. And the reason for that is that these signs and symptoms of magma moving can be really subtle, especially at the start. They can be magnitude 0 or 1 earthquakes. It's very, very rare to see an earthquake larger than magnitude 3 at a volcano. In terms of deformation of the ground surface, that usually is something on the order of a centimeter or maybe even a couple of millimeters. And you really can't see that unless you have enough GPS instruments that are trying to tell you where they are. And also they need to be in close because that deformation is oftentimes focused right on the volcano. So that's kind of the monitoring goal for these very high-threat volcanoes is to build up the instrumentation so that we can see some of these things. To give you a sense of what the instrumentation that we put out looks like, this is a fairly typical seismic station with GPS receiver. This is the GPS receiver. This is the antenna up here. And there's a seismometer buried at the corner of this enclosure. This enclosure here has all the batteries in it and the solar panels and the radio. And this site's been out there for 7 years now. It's near Newberry. It gets a lot of snow. It gets lots of lightning. And so far, it's not been fried. It's also painted in a very attractive color of brown, which we selected after consultation with the Forest Service, which told us they didn't want just raw metal up there because it would be shiny and that would potentially cause visual disturbance for people who are walking around. Here's a picture of an atypical seismic station. This one is our highest elevation site that we operate. I think, kind of anywhere actually, Mauna Loa's got one or two that are higher. This is at 11,000 feet on Mount Rainier. You can see it's surrounded by pretty significant glaciers on both sides, and this is what it looks like up close and personal. It looks very different from the other site because we have to reinforce it with all kinds of pipes and stuff like that because it gets buried by about 40 feet of snow each year, and it stays that way for most of the year, about 9-10 months out of the year. And we have to service that site quite a bit as it is, but it's a very important site because it's close. And then this is a close site at Mount St. Helens. It's actually on top of the vent from 1980, and this was a fairly low snow year, and still we had to go out in March to unbury it because we lost the signal. And this is something, it's just part of the deal of working at high altitudes and in close at volcanoes, is that we have to figure out some way of making our instrumentation work. In the event that we don't have all the instruments that we need out at a volcano, we have a couple of fallbacks. One is this platform that we call colloquially a spider, because it kind of looks like a spider. It's got these arms that stick out on both sides. And this can be sent out by helicopter. There's a sling hook right here that hooks onto the long line of a helicopter, and the helicopter pilot can fly it out to where you want it to be and be in and out of harm's way in about 10 or 15 minutes. Whereas in the olden days, you had to have people out there that were digging holes and pouring cement and things like that. On this platform, you can hang a bunch of instruments. There's a seismometer right there. There's a lightning detector for looking for lightning that's caused in ash clouds. Infrasound for detecting in the air explosions. And then there's also a GPS antenna that can tell you if the ground is moving or not. To give you an example of the importance of having networks out there, I'm going to show you Newberry, which is this volcano in central Oregon. It's a really fascinating volcanic system that Julie Dolly-Nolan's geologist here has unraveled a lot of the volcanic history there over the last several decades. And this is a volcano that we initially thought was actually pretty dead. This is a map that shows one seismic station. Is operated by the Pacific Northwest Seismic Network, which is our partner in all of this. It's operated out of the University of Washington. So there was just this one triangle out there from 1982, I think, to 2011. And these yellow dots are the 10 earthquakes that were located out there during this entire time. In 2011, we installed an 8-station seismic GPS network. You saw one of those in a picture a couple of slides ago. And just in the 2 years after that installation, this is what we saw. So not like thousands of earthquakes, but getting close to hundreds of earthquakes. And we've learned that Newberry is actually one of the more seismically active systems that we deal with in the Cascades. And we had no clue about this before we put this network out there. This is sort of an extreme example. Newberry turns out to be a place that absorbs seismic energy, and there's all kinds of reasons for why that might be. But this is just illustrating the importance of having stations out for a long time. The last part of our sort of core function of focus is community preparedness. And this really stems from one event, at least in the USGS it does, as a strategic pillar of importance. And this one event was an eruption in 1985 in Armero, Colombia. And that eruption was known about. There had actually been unrest that had been building for several months. And there were scientists out there that were tracking it. When the eruption started, they saw it. And they started seeing some signals of a mud flow starting to develop, which in volcano world we call a lahar. That's an Indonesian word for mud flows, and Indonesia gets lots and lots of mud flows. In this case, what generated the lahar was some hot rocks landing on top of an ice cap. And the ice cap, Naval de Ruiz is ice-clad, and the hot rocks melted some of that snow and ice and started this mud flow, or this lahar, going down a river. 2 hours later, it got to the town of Armero, which used to have a lot of houses in this picture, but now it doesn't. And 20,000 people were killed. Over 20,000 people were killed. And the reason why they were killed boils down to there was a disconnect between the scientific operation where people knew about this and the folks on the ground. There's a whole bunch of reasons for how that disconnect happened. They don't all or very many or any really have to do with the scientists themselves. It was just this communication chain didn't exist for a wide variety of reasons. And so that really is the underlying reason why there's a lot of emphasis now on community preparedness. Lesson learned, if folks don't understand the hazard and aren't ready to hear you tell them about it when there's something happening, then a disaster could happen. So in Washington and Oregon, we've been working fairly hard on facilitating the development of response plans, or actually these are coordination plans, for all of the very high-threat volcanoes. These coordination plans are actually the domain of the state emergency operations or emergency management divisions, and are also better served if they're really led by stakeholders from counties and cities and tribes and whatnot. So our role is really to facilitate and nudge things along and be subject matter experts. And it's been really gratifying to see that this work has led to officially sanctified plans on just about every one of the volcanoes. But it's taken an awful lot of effort on the part of many stakeholders to get these plans to pass. Something that we've been doing internally in the USGS Volcano Science Center is to clean up our alert level language. It used to be, each observatory kind of came up with its own way of communicating alert levels. At CVO, when I arrived in 2003, we had a type 1, type 2, type 3, something like that. In Alaska, it was the color code, green, yellow, orange, red. Down here in Long Valley, there were a couple of different colors in addition to all those, and Hawaii had its own system. And we were getting feedback that was difficult to understand. There was sort of confusion that people were having about these different messages. So we got our act together and came up with this kind of compromise, which on the left-hand side, this is for the ground and matches exactly the National Weather Service language. That was feedback we got from stakeholders that they were used to the National Weather Service. Of course, the National Weather Service is now contemplating changing the normal advisory watch warning, which is I'm actually glad about, because watch and warning always confuse me. I just have to think about, which one's which. And then alert level is green, yellow, orange, red for aviation. Something else we've been doing is working on producing products that are based on our volcano hazard maps. And we have hazard maps for all the volcanoes, but they're a little bit technical and a little bit hard to understand when you first look at them. You can get it if you look at them for a while, but what we decided to do is work with stakeholders again to come up with these what we call simplified hazard maps, which break hazards down into this near field area where you really don't want to be when a volcano is waking up or active, because this is a place where things could get to you within 30 minutes and there's no warning and things like that. And then these more distal areas, which are largely places that are subject to these mud flows or these lahars. And we've rolled that out for all of the volcanoes. And then finally, folks in our office, Carolyn Dreger most notably, have put together a media plan for us scientists with guides for preparing interviews, with tips for things to say and things not to say in interviews, and also just kind of practice. How do you practice? And this kind of thing is important because you never know when this is going to happen. And this is our conference room. And when Mount St. Helens woke up in 2004, all of a sudden our conference room became a place where we were having press conferences, 1, sometimes 2 times a day, that were nationally televised. And so there were a couple of us that were just sort of taking turns as subject matter experts in front of the microphones. And it's really helpful to have something there to tell you, don't say that word that you're thinking about saying. And more recently, we've had some pretty entertaining examples of the media sort of taking off on things. And actually, it's not media, it's social media taking off on things. So this is a plot that shows all the earthquakes that have been located at Mount St. Helens from 1987, down there on the left-hand side, to 2017. And it shows them by depth. So 0 is sea level, -2 is above ground, above sea level. And this goes down in depth to about 10 kilometers. So this shows all the earthquakes. Here's the 2004-2008 eruption. And then we've been in this period of sort of quiet since then. And things have evolved in terms of where earthquakes are occurring. And every once in a while, you get a little uptick. or a little swarm. We started calling them upticks because swarms, nobody really knows what that means. Is it a swarm of bees? Uptick seems to get people's attention. We don't issue any formal statements, but we have a Facebook account. There's a USGS Volcanoes Facebook account. And we feel like all this data is available in real time, and so it's important for us to be providing interpretations for folks. So we put a little paragraph out there that said, there's been an uptick in earthquakes, and this is part of a process that we think is leading to the next eruption at Mount St. Helens, which is years to decades down the road, and we've seen these things before, and things like that. And before we knew it, it was on CNN headline news, right there below articles about President Obama and also this awful fire in British Columbia. That just happens. And then the local media showed up afterwards wondering, well, what the heck is this all about? Do we miss a story? And it's like, no, there's no story. This is just an uptick. But it's important to have an understanding of how to do media interviews. The last thing on community preparedness is that we are realizing that any future eruption that's going to happen anywhere in the lower 48 is going to be handled through what's known as the incident command system. And that's something that was developed in California to handle wildfires and has since spread like wildfire to all 50 states to mainly handle wildfires, but also to handle other large disasters like hurricanes. All of the hurricanes that happened last year were dealt with incident management teams, level ones. And it's pretty clear that's how the next crisis, volcanic crisis, is going to be handled. And so we are educating ourselves on what this thing is. What is the incident command system, and how does these weird scientists tap into it, the scientists who want to go to the volcano when the whole incident is geared towards keeping people from doing that. That's just an ongoing process that we're working on. So in the last part of this talk, I thought I'd walk you through a couple of tangible examples of how all this stuff interacts and how all this works. And when I did this talk at noon, I ran long and I had to skip through a section. I was told, don't skip through that section, but now I've run even longer. So I'm going to skip through this first section. I'm going to focus on Mount Rainier. There we go. Okay. So Mount Rainier, I mentioned this before, is a place that has lahars. Lahars are these volcanic mud flows. And here is the town of Orting, which is about 40 or 50 miles away from Mount Rainier by stream. And this whole flat plain here is covered in deposits from a very large lahar that came off of Mount Rainier about 1501 is when geologists think it came through. And people, when they're excavating foundations to build new houses, are unearthing these large trees that were brought down by that lahar. And were that to happen today, it would be a bad thing. Just to give you a flavor for what lahars look like, this is a video that was taken at Mount Rainier back in 2015. This is a very small lahar. And actually at Mount Rainier, we're splitting a hair in terms of terminology because people in the Mount Rainier area have heard the word lahar, large lahar, a lot. When small lahars happen, they get freaked out when they hear the word lahar. And so we started calling these small things debris flows. And so here is a video of a debris flow that was caught by a tourist.
This is crazy.
And I should say, this is very much like the kinds of mud flows that happened here in California just a couple of months ago in the wildfire areas.
Get back, I'm scared. This is all dry. There hasn't been water down here, and look at all this. The water is like black.
It's both. It's you call it mud, but there's a lot of water. It's got a lot less water than mud. It has a lot of sediment in it, and that sediment gives it the consistency of cement. And the cement can carry these big objects like that huge tree there, and also all these rocks in it. And that's one of the things that makes debris flows, lahars, mudflows, really destructive is that they have
Look at that tree. Look how tall that is.
they have these battering rams in them, and one of the misconceptions is that a lahar comes through and it's like a flood, and floods come up and they do damage in terms of soaking stuff, your sofa or your walls and things like that. But the floodwater goes away, your house stays around usually. But with lahars, that doesn't happen. The house will go away if a lahar is there, and that's clearly what happened at Armero back in 2015. So this hazard's been known about for a while. 1967, the first hazard assessment was written for Mount Rainier. Actually, the first modern-day volcano hazard assessment in the lower 48 was written back then, and by actually a USGS geologist named Rocky Crandall, and also came up with some hazard maps and things like that. We now have a more refined understanding of the Lahar hazard. This is a map that shows 3 of the largest ones that have come off of Mount Rainier. The Osceola from 5,600 years ago, the National from about 2,000 years ago, and the Electron from about 500 years ago. So 9 of these are known to have occurred in the last 5,600 years. 8 of them were associated with eruptions. So that's the good news. It means most likely scenario is the volcano erupts and then you get the large lahar. You don't have to sort of worry about it too much. But there is one exception. There's one lahar, the Electron mudflow, the most recent one, 1501, that does not appear to be associated with any eruption, at least anything that left there's no geologic record of it. It's possible there could have been some sort of steam explosion that there would be no record of, but it's by far not the most likely scenario, but it does leave open the possibility for something that's called the unheralded lahar, the bump in the night, something that could happen spontaneously. There are about 90,000 folks that live in lahar hazard zones at Mount Rainier, and the estimate is that if one of these spontaneous lahars were to let loose, there's about 60 minutes from when it starts here to when it would reach the town of Ording. And Ording, it's not 90,000 people in Ording, but there's several tens of thousands of folks there. So in terms of research, here's a topic. How stable is the edifice of Mount Rainier? A couple of USGS geologists dug into that question back about 15 years ago or so now. And Carol Finn from the Denver area and Mark Reed from here, as well as Tom Sisson, and Jim Valance and some other folks that mapped out the geology of the edifice, established that there's this part of the western flank of Mount Rainier that's composed of fairly altered rock, and it's also very steep. And Mark Reed has done some modeling and showed that this is the place that is the most unstable part, potentially unstable part of Mount Rainier. These other sides are plenty steep, but they don't have this altered rock problem. And there's other places that are altered, but they aren't quite as steep. So this is really the place where this kind of thing could happen, that happened at the Electron mudflow in 1501. And here's a picture of what it looks like in time. So there's researchers at CVO who have taken that red area and have put it into a model that's just been developed that allows one to start a mass of rock and ice, start it moving, and see how far it goes and how fast it goes. And I'm going to show you some simulations from that. So here is that patch, the red patch that I showed you before on the west flank of Mount Rainier. And the volume in there is about 260 million cubic meters, which is a large lahar. That's a pretty large one. Not the largest that Mount Rainier's ever done, but that would certainly get people's attention. And now I'm going to show you their results. This is Dick Iverson and David George from our office. And so this is 2 minutes after the inception. So the inception started up here, and here it is moving this way and moving this way. The important thing that their simulation has showed is that this lahar has split into 2 drainages. It's going this way, and it's going this way. And you'll see the importance of that in the next slides. So here's one going down here, and this is the Nisqually entrance. That's the place where people go into the park. That's the closest place where there are year-round residences. There are some hotels there and things like that. And then there's also this town of Ashford. So that's at 10 minutes. 20 minutes, it's reached the low-lying areas of Ashford. and then keep paging it forward. There's another town over here in about 40 minutes, and then at about 70 minutes, it gets to Ording. So this will get 2 different drainages going, 2 different sets of communities. And it's a, like I said before, it's not a likely scenario for how we would get a Lahar, but it's possible. And so there's some questions about what do you do about that. So here's when the monitoring part comes in. In 1998, USGS worked with Pierce County, which is the county that has jurisdiction over much of the, this western flank area, to install a system of 5 instruments on these 2 drainages that there's a couple of tripwires there that are put at strategic levels. And the basic idea is that if there's a Lahar coming through that's large enough to reach Ording, it'll take out the tripwires and it'll make a lot of noise, and that will trigger an alarm. And so that alarm system has been running for 20 years. There's never been an alarm, which is a good thing. But it's at this point getting old, and it's a fairly crude system. Now, what these are looking for, that video that I showed you before, this is a seismic record from that debris flow, that little dinky Lahar. It lasted for a couple of hours. That was recorded by a station that was up on a ridge right over that river drainage. Other stations that were just a little further away didn't see that signal at all. And the physical reason for that is that it's a surface flow. So a lot of the seismic energy that's being created is staying in the surface. It's not going into the rocks. It's not going out to where our seismometers are. And so one of the things you need to do in order to be able to catch these things is you have to put seismometers out that are close to the drainages, and you have to have more than just that one. And so that has started informing our strategy for the next iteration on this system. And all these orange dots are aspirational at this point. We're again working with Pierce County to develop this system. It's not a trivial prospect at all. And we're also expanding it down to this other drainage where we've learned things can get to populated areas a lot quicker than the 45 to 50 to 60 minutes that we were thinking for Ording. So that's the monitoring piece. Then there's the community preparedness part. So here's the message. These scientists have figured out Lahars can happen at Mount Rainier, have happened in the past, have reached populated areas. What do people do about it? And that's a really important part. So we've been doing a lot of things with the media, with working with educator guides, with taking folks out on trips, going to job fairs, going to emergency preparedness fairs, working on these coordination plans, doing tabletop exercises, and working on policy and things like that. One of the outgrowths of that is this really cool drill that the town of Ording has been doing for at least the last decade. It's a drill on a specific day. I forget what the day is. Sometime in May, and the target is that the kids need to get out of their schools and to high ground within 45 minutes. That's the sort of time window where that system that's in place now, the USGS put in, will give about 45 minutes of warning for people to get out. So that's the bar. Get everybody out in 45 minutes. This is a picture that was taken from the drill just this last spring, and that's their goal is to get out in 45 minutes. In 2017, this was the first time that all the schools participated, from kindergarten on up to 12th grade. So about 2,000 kids, and they made it. It was a successful exercise, and the elementary schools are one of the fastest kids because they skipped all the way. And a lot of the high schoolers who have done these drills a number of times now were ushers or were there cheering the little kids on. And it became kind of this cool community event. And so it's turning a potentially scary message into kind of a fun thing, and also having people be empowered. And that's, I think, one of the things people have learned everywhere around the world is that you can't just give bad news. You also have to say, here's what you can do to help yourself and help others. And this is also good preparation for this community for other disasters, not just Lahars. So all this leaves us with some hard questions, which we're going to be working through for the next bunch of years. One is, how much should society worry about large lahars at Mount Rainier? It's 1 in 500, 1 in 1,000 years if you sort of go by averages. And that's kind of a long time to be doing these evacuation drills. So there's sort of balance to be struck in our messaging between making sure people are aware of the hazard while not scaring the pants off of them, and also sort of having them have a perspective for where do you put this in the range of all the things there are out there to worry about. With this new system that we're putting in, we're going to have capabilities to provide warning quicker than we do right now, but they're not going to be as precise. We won't necessarily know. We'll know there's going to be a big bump. We'll know there's going to be a big landslide or something like that, but we aren't going to know how big the thing is until probably 10, 15 minutes after it's happened. And so the bigness is important because that tells you how far it's going to go. And so what do we do with that first notice when we see this big noise but we don't know what's going to happen just yet? Do we tell people about it? If so, what do we say? And is this sort of like a ready, get, set, go? Is this like a tsunami advisory watch warning, which is what the NOAA tsunami warning centers do? And this is where we really need to be working with emergency managers, because they're the ones that the messaging really, really matters. And then also, who sends out the alert? Do we do it? Do the counties do it? Do the state do it? Does the National Weather Service do it? Does somebody else do it? All that stuff has to get worked out, and it has to get worked out well ahead of time. And then finally, these large lahars can reach communities that are close to Mount Rainier, that have year-round residents. They're not big communities, but I think we've all learned that there's no such thing as acceptable loss of life. So with 10 minutes, we're not going to know what we're dealing with when we see the big bump in 10 minutes. We'll just know that it's sort of going there. So can we design a system that gives robust alerts to those folks and gives them at least a couple minutes to get to high ground? And all this is being done with keeping this example in mind of our marrow and the importance of doing this. So that's CVO, and back to these happy people. And this final picture is just a little defensiveness that, yes, this is from Mount St. Helens 2005, and yes, low probability, high consequence events can happen in the Cascades and will happen again. Thank you.
Thank you, Seth. We have time for some questions. There are 2 microphones set up if anyone wants to go up and ask the question.
Hi.
Yeah.
This is a strange position to take, and it could apply to everybody here in the Bay Area, but there's bad places to live, and we're trying to do all this mitigation to protect people from living there, but they decide to live there anyway. How far do you go with that?
Yeah.
I mean, I understand there's a grayscale and there's a limit to everything, and heck, we probably shouldn't be living here in the Bay Area because we're all going to get nailed by an earthquake one of these days. But how do you balance that in a practical way?
Yeah.
Because you've got all these limited resources and competing interests, and anyway,
yeah,
it seems like a really hard problem.
Yeah, it is a hard problem, and there's a couple of avenues to go sort of to talk about that. I guess the thing I think about, because the earthquake, the big one, is the one that would be really horrible, and I think about that in terms of why am I living in Vancouver, Washington, and the answer is it's a great place to live, and this is one of the things that can happen. And just because it happens doesn't mean that I'm going to die. In fact, it doesn't mean that most people are going to die. Probably 1 or 2% of the people, and that's going to be horrible. But the vast majority of folks in the Pacific Northwest are going to survive. And then you've got to prepare yourself for surviving, because then you're going to be dealing with weeks or months of not having food, not having water, not having garbage disposal or garbage service. And so there's a positive message that you can do stuff to get yourself ready to survive. In the case of Orting, there is a potential circular argument that could be made that in putting this system out, we have helped people feel more comfortable about living in a place that's hazardous. And in some ways, we're making the problem worse. There's no good evidence to support that. And either way, it's not something that anybody's really looked at. And my personal feeling is that the rate at which people are spreading out, that's like if it's a factor, it's not factoring into why Ording is exploding in population. It's exploding because it's a cheap place to live in the Puget Sound area, and it's still pretty close to Tacoma. And there's another way of looking at it, which is there's this awful landslide in Washington in 2014, the Oso landslide that killed 43 people. And there's all kinds of recriminations back and forth about whether or not people knew that was a slide-prone area, whether people knew that was going to happen, and could there have been any kind of warning that was going to happen. In that case, really tough. People right there, and you can't monitor the entire world the way that slope would have needed to be monitored to be able to give warning. So in this case, with Mount Rainier, there is a known hazard. It's a scientifically plausible scenario that part of the volcano could fail. And so I think that puts it on us to try to develop a system to try to give people some warning. And if in the end we're not successful, at least the important thing is that we've tried our best and we've done our best to give people information that they need. For the folks that are like 10 minutes away, 20 minutes away, they've been there without a system. And so I sort of look at it as informing the folks who are there to give them some sort of power. So it's it's not a long answer, but the short answer is you're right. It's a really tough set of questions, and that's where scientists we can provide information, and we can develop systems to help mitigate things. But we're not social scientists, and we're not sociologists, and those are the folks that and philosophers. Those are the folks you really need in the mix to be grappling with those really hard questions. And we have opinions as scientists, but who are we? Yeah.
So in the case of the, I don't know if this is working. Yeah, there it is. In the case of the Lahar without the eruption, so what's the mechanism for that? Do the rocks get really really hot and melt the snow and ice, or do they just start falling off? What is it that happens in that scenario, at least what you think might happen?
Well, the scenario that was modeled is that it's an instant collapse. So that's kind of like what happened at Mount St. Helens in 1980. That was a large landslide. That obviously was preceded, in the case of St. Helens, by magma coming into the volcano and making the whole thing unstable. But it was really gravity that caused that failure in the end. So at Mount Rainier, there's a physical set of reasons to believe that it could just happen because of gravity. There doesn't have to be anything additional going on at the volcano to cause that to happen. Now, it's more likely if there is something happening at the volcano. That's been our experience around the world with these large lahars, is that they almost always happen in context with a steam explosion or some intrusion coming into the volcano. And it's certainly possible that could have been going on at Mount Rainier in 1501 when the electron mud flow went off. But it's also plausible that it could have just gone off on its own. And we're still looking at a situation where there's a gravitationally unstable slope that's made of pretty weak rock. And so it could just spontaneously go.
So that big piece you were showing in red, it
Yeah.
might just fall off, is what you're saying.
That's the possibility.
So why would all the ice and snow melt if it's just rock falling off?
So there's a turbulence involved in the mixing, and there is some hotter rock that's inside, and there's also snow that can get mixed into it and incorporated into it. But it's also true that we don't know that it would liquefy. So the scenario that I showed assumes that it's a wet flow, that everything liquefied, that the ice and the snow and the altered rock in there did eventually mix up and create a liquefied concrete-like or cement-like flow. But it's possible that that wouldn't happen. It's possible there would just be a big noise and it would just go flump, and then there wouldn't be a lahar. And that's part of the difficulty in our using the initial signal as the thing that says, okay, there's a Lahar coming, get out of town, because we have to wait for a while to see if there are instruments downstream that start picking up things. And it's possible that it might not. So, the real problem with low probability, high consequence events is that there haven't been that many low probability events, by definition, almost. And so we don't know a lot about how they start and what they look like. And some of these questions that you're asking about, like, will the ice liquefy? Can't 100% guarantee that it would.
Thank you.
Yeah.
Question, would you go back to the map where you showed the simulation of the Lahar coming down onto the town? I'd like to say thank you for your work at the USGS, and I'm very convinced of the value as a taxpayer.
Oh,
so mission accomplished there. Back one more. Back one more. At the very low right, you mentioned that there were a couple of hotels there. It was the entrance to the park.
Yeah.
I'm going to ask a couple of pointed questions.
Okay.
Have the insurance costs gone up for those hotels? Have the land values in that area been suppressed? Are the real estate agents and the Chamber of Commerce behind that? And finally, has your work resulted in a pushback, or I'll say a denial of geology science? Talk a little bit about that.
Yeah, I'll take those point by point. Great questions. So the first way to answer that is that Lahar hazard maps, or hazard maps, volcano hazard maps, were made up for Mount Rainier and all the other volcanoes in the Cascades. Not made up; they were published and in the 1990s. And those have been used by land use zoning to create zoning laws. So they factor into things like floodplains. And one of the things that we've been told by county managers and things like that is that when we upgrade our hazard maps, they want to be involved in the loop right away, because these lines matter quite a lot. But the lines are there, and they are already mattering. So in terms of the folks here, sort of the hotels and things like that, they hopefully should know already that they're in a zone. What's different now is that this simulation is showing that this unheralded Lahar situation can get to them fast. And you raise a really excellent point, which is that we have to think about how we're going to talk with these folks about that. And that's where messaging comes in, and that's where we need to work with our county partners to sort of strategize on that. And you don't want to get into a situation where people feel like you're holding back on them. So we're not holding back on this, but we do need to think fairly carefully about what we're going to say with this, and how people might receive it, and then what are we doing about it. But yeah, good questions. Oh, sorry, over here.
When I read about the volcanic events throughout the world, such as in Indonesia and Italy and South American places, usually the biggest effect has been explosive effects like the ash, which is the most serious, and then lava in Hawaii, but that's not really that serious to most people. It's slow. But you haven't talked about that effect in the Cascades. Is that a negligible probability? That's why your Lahars are so much more discussed than any possible major explosion of ash?
Yeah, so ash hazards are a real issue, and I did mention them when talking about Glacier Peak. And Mount St. Helens, that was a big deal, was the ash story, downwind. So the hazards are the Lahar hazards and the ash hazards. Those are both the longest traveled impacts of an eruption. But they have different types of impacts. The ash goes up in the air. It's a bad deal if airplanes get caught in that. So there's all kinds of short-term things. The Federal Aviation Administration has told us that they want word of an ash-producing explosion within 5 minutes of it happening anywhere in the United States, which is a high bar. But they want time for airplanes to get out of the way. And also, there's the downwind impact. Mount St. Helens, Yakima, the day turned to night. They got, like a foot of the stuff. And how do you get rid of it? And that was a story for weeks afterwards, is how do you get rid of it? And what is it doing to my crops? And what is it doing to my animals? And how do we breed it? So all those are problems. The Lahar problem is an instant problem in the sense that it can get to places in a hurry and cause kind of totaling type of damage if you're in the way. But then also you have this much longer term issue of now you've altered the amount of sediment that's in this drainage system by a lot. You've put in this case, 250 million cubic meters of sediment into this whole drainage. And that all has to make its way down to the ocean, basically. And that can take decades. And while it's doing that, it changes the drainage in a way so that the carrying capacity is a lot lower. Basically, you've raised the bed of the stream by quite a bit, or the river, and it makes it a lot easier to flood. And then the river starts snaking around and it erodes its banks, and people who are living on the sides of it get all flooded out. And it also makes a problem for fish. All that's been playing out at Mount St. Helens. There's a river valley called the Tule River, and a lot of the debris avalanche and the Lahars that came off of the volcano that day went into the North Fork of the Tule River, and there's still so much sediment in there. There's no fish run is going to be going up that stream anytime soon. And it's caused such a problem with flooding downstream that the Army Corps of Engineers has built this large structure to catch a lot of that sediment to keep it. So you're right that ash is an issue, and I didn't really focus on that much because this Lahar issue is one that's sort of illustrative of all the things that we do in the CDO. But could
you didn't quite answer my question. What's the probability of the explosion where the ash problem is a problem in the Cascades of Mount Rainier? My daughter happens to live 50 miles west of Mount Rainier, and I'm worried about whether she has expected an explosion someday.
Yeah. So for Mount Rainier specifically, the short answer is it's not likely to explode. It has small eruptions. And there could be a little bit of ash if the wind's blowing the right ways at the right time. And it's sort of the same thing as Glacier Peak. So that map I showed you is where we're aiming at in terms of how to establish the probability thing, is looking at the most typical eruption, looking at wind fields, and kind of forecasting that out. But the most likely scenario is Mount St. Helens, frankly. That's the one that will give you the ash.
Thank you.
Okay. Yes?
If you had a very large volcanic event up there, considerably larger than Mount St. Helens, what would the impacts be down here? Apart from ashfall, it looks to me like you'd have considerable secondary social and economic impacts. I mean, a disruption of the electrical grid, ports closed, and just strain on responders from here as being the next closest place of assistance, and so on and so forth. But what would have to happen before the secondary impacts were felt significantly in California?
What, in terms of, what do you mean by
Well,
that?
what I'm saying is, we know from the Cascadia earthquake scenarios that even if we don't feel a vibration, the social and economic impacts down here are going to be very, very, very substantial. You lose the electrical grid up there,
Right.
What's going to happen to power down here?
Right.
But, I mean, what's the scenario with a large volcanic event, and how large would it have to be before we would see those sorts of effects in California?
I couldn't give you a number for how large. I mean, I think Mount St. Helens had impacts up and down the coast because of disruptions like the Columbia River. The port of Portland was inaccessible for a week and a half because the Columbia River was non-navigable.
Right,
Because
but
of
I mean,
the
if you had a
hard
port that went out for 6 months or
Yeah.
something, if Tacoma were...
Right. But then, like you mentioned...
Then that traffic is going to have to come through here, or...
Right. And then the power grid, you mentioned that. I mean, that would be a problem. In a really big eruption, that would be a fairly significant problem. There'd be mutual aid for sure that we'd be needing. But yeah, I mean, I think in terms of like ash coming down here.
No, that's not done.
If it was a large enough eruption and the winds were blowing the right direction, I'm pretty sure that some of the Mazama eruption, a little dusting came down here. Wouldn't surprise me if that was the case. But Yeah, it's a little difficult to forecast that kind of thing and to say, how much bigger, what it would be like. Like the Glacier Peak eruption, which was, say, call it 4 or 5 times the size of Mount St. Helens. That's in a place where there's really not many people and not much infrastructure, so it would have been a big deal east. But there wouldn't necessarily have been the need for mutual aid like there would be at Mount Rainier. So.
We have a question.
I was going to say it's a good time to think about buying electric vehicles because you don't have that ash clogging.
Can you use mic? Yeah.
Can everybody hear me?
Well, it's for folks online.
Okay.
You're on.
Okay. Recently, there was a Goddard Tunnel. They put the Goddard Tunnel. Oh, I'm sorry. In Switzerland, right? They've been tunneling through there. I was thinking a good idea for escaping this kind of thing because 45 minutes may not be enough if it happens in the middle of the night. And if it's raining, that'll complicate things further.
Yep.
Yeah, electric train underground seems to me as if you want to stay in that hazardous area.
There's other reasons for having electric trains underground besides ash, but yeah.
Yeah, absolutely.
Yeah.
All right, that was more of a statement than a question.
Yeah.
You had Crater Lake on your list. I guess I naively assumed that Mount Mazama had done its thing, and now we just have this beautiful lake. Can you give us just a brief status update on that area since it was one of your red zones?
Yeah. So it's there because of that large eruption, and there hasn't really. There's been a few in the 100 years following that, but then there really hasn't been anything. Certainly for the last 6,000 plus years, that kind of is an illustration of the scientific method or the scientific principle is you come up with a way of comparing volcanoes, and then you have to apply it equally. So if you erupted in the last 10,000 years, then you get a point.
Oh, okay.
And so that's so if we wait for 3,000 more years and Crater Lake doesn't erupt, then off it goes. But we do have a fairly sparse network there. There's 4 seismic stations, 4 GPS. We see the occasional earthquake. There's not been any hint of deformation. So there's not. Yeah, there's a little bit of gas accumulation of gas at the bottom of the lake that the Park Service has found with a little submersible robotic thing that they sent down a couple of years ago. And so it's sort of interesting to think about. Well, where's that coming from? And it's probably not dead. But it's probably going to take a long time.
Not much activity.
Not much activity. Yeah, scientists take a long time to answer questions shortly, but not much activity.
Okay, well, let's all thank Seth once again. And I'll just remind you again of our next public lecture on March 22nd. Thanks for coming.